It is my pleasure to introduce today's speaker, Alex Henzen. Alex brings a wealth of knowledge on the topic of display technology. With extensive experience in display panel design, he has made significant contributions to the display industry. Today, he will share insights on a technology called SAVT, Sampled Analog Video Transport, delivering high accuracy and perceptually error-free images. Welcome, Alex.
Thank you very much for the kind introduction. I'm going to talk about sampled analog video transport and have high accuracy and perceptually error-free images. I've made the presentation together with a couple of co-authors, very well and renowned people in the field of electronics processing. My own history is in displays. So what I'll be talking about is initially an introduction of the SAVT basics, perceived accuracy of a display, then talk about better electro-optic transfer function handling and looking at FIR filtering to correct any possible errors in the transfer. Then look at model verification and conclude the talk. So HYPHY is a semiconductor IP company, so we're building IP that has to do with sampled analog video transport, which is a way to send 10 times more video information along a digital than a digital video transport. Basics of SAVT, I'll take you back to where we are at the moment. So high performance displays are hitting a bandwidth wall. That means that increasing frequency or refresh rate requirements for gaming, 4K and maybe even 8K television and light field displays are requiring more than the physical bandwidth of P2P, which is the TCON to display driver IC channel can handle. Ways to solve that have been seen at the show at the moment. So we can solve that by increasing the number of parallel wires that lead from the video source transmitter to the display driver IC receiver. But they usually require more than only that. They require things like equalization, and they may even require compression of the video source before it is turned into the same analog D2A converter to the display driver, which is an expensive and area consuming and power consuming direction. So how does sampled analog do this? Well, it's 10 times faster, or as I will show, maybe even 10 times slower than serial deserial. This lower trace here is a representation of 3 pixels being represented by 30 bits of data transmitted in a serial transmission. The same 30 time slots are enough to transfer 30 times more or 10 times more pixels, so 30 pixels in the SAVT case, because each time slot 1 pixel level, subpixel level is transmitted. So we can transmit 30 pixels instead of only 3. Conversely, we can also send 3 pixels at 1/10 the speed, which is also important. So it has at least a 10 times enduring speed advantage. The implementation in an actual display is also pretty simple. This is a view of a legacy display system, which the input on the left-hand side, then you've got a system on chip and a transmitter here, digital signals being transmitted to the LCD panel on the other side, and you've got a bit-perfect source driver input, but at an 8-bit D2A converter level. SAVT looks pretty much the same. There's not much difference. The only difference here is that the transmission of the analog system takes place here at the place where the SerDes used to be here. And so it is a SerDes variant transmitting analog signals to the LCD panel. But thing to be noted is it does so at 14 bits resolution, not 8. There's a bit of an intermediate of perceived accuracy. Everybody thinks, well, a video transmission should be error-free, no defects, because we're treating our visual system as a machine. But it isn't. We are perceptually completely different from a machine, and I'll show you why. If you look at a digital transmission, there's usually a machine component in there, like a clock or a intermediate data setting. And if one of the bits drops, then you run the risk of having a catastrophic failure. So you might lose sync, or you might lose other stuff. Human recognition doesn't care at all. If you miss 1 in a billion pixels, every 40 frames you'll see a pixel blip out of control, but that's only once every 100 milliseconds or every 25 milliseconds. Absolutely unnoticeable. So we accept that. Also, we do a much better electro-optic transfer function handling. As you see here, until now, what you have is a 10-bit input into the video system, because a video source has 10-bit resolution, but then we need to process. We need to do gamma correction, HDR, mapping, lookup table for all sorts of image corrections. And then, after doing 10 or 12-bit, in the best case, transformation lookup table, then we go back to our 8-bit transmission system and transmit the 8-bit plus FRC data to the display driver and display that on our analog panel, which doesn't seem great. The SAVT system works differently. We get the same 10 bits coming in, but we handle the gamma, HDR, and also the TV curve adaptation for the display in a 14 or 16-bit environment. And then we don't need to cut down to 8-bit to transmit. We transmit the entire 14 or 16 bits to the display driver to drive the display. And that means we have a much, much better definition at the display side. The reason why this is important, among other things, and there are 2 slides to try to explain this, is that a traditional way, the display driver has the D to A conversion and the conversion to the transmission voltage curve of the display in a single position, and it doesn't care and it doesn't know whether a column is red or green or blue. But there is a difference between a red and a green and a blue pixel. The transmission voltage curves are slightly different, not hugely different, but slightly different, and that means that your adaptation, so your correction in the video stream needs to be upstream. So you need to have the 8-bit transfer to correct for the slight disparity of the red, green, and blue transmission voltage curve. So you can choose actually to take for granted that they're not accurate, or you can do a digital interpolation of the correct TV curves. So it's always suboptimal. And in the case of SAVT, you don't have that problem because every color is corrected by 14 bits. Now, if then, as a consequence, the color reproduction would be a straight 10 bits to 10 bits array, then 10 bits would probably be enough to display colors, but it isn't. So the TV curve I just mentioned is not a straight line, but it's slightly varied. But in the classic display driver, this is handled by the physical D2A converter, which has typically something like a correct 8-bit correction, and it's more or less accurate. But then things become more difficult. You have to correct for the gamma curve, no matter what. But this gamma curve is not a linear system, but far from it. It's a very nonlinear area, and this part here, the dark area, is much less than 100th the slope of the actual voltage curve. In the past, in the distant past, we used to do the gamma correction in the display driver as well, but that is not the case anymore. We now do that in the system on chip, and so we have to handle all that in our 10-bit subsystem. So the combination of these two curves leads to this curve, and HYPHY now uses 14 bits to D2A to compensate both curves at the same time by using a 10 to 14 or 10 to 16 bit lookup table in order to get all that correctly displayed. And that means we can now correctly reproduce the low end of the gamma correction curve by using 240 microvolt per step instead of the usual millivolt. There's a nice addition to this. This means that theoretically we will be able to display 281 trillion colors in the final display. It may not mean much, but I can guarantee you it means a lot to the people selling TVs. So we've done a bit to look at the background of all this and see how we can make sure the transmission is done accurately instead of just 14 bits resolution, but inaccurately. So we did look at noise and distortion in the transmitted signal, because we are transmitting an analog signal that needs to be taken care of. Noise, we consider statistical sources like Johnson noise, shot noise, etc. They are small noise sources, and they're typically below 40 microvolts. We don't really need to take them into account, and if we did, they would average out over time. And then there's distortions in the signal, like reflections, like attenuation of the transmission line, bandwidth restrictions, and these can be handled in various different ways. So in manufacturing, you can handle reflections. Reflections typically occur when transitions between two conductors occur. Sampled analog means you're sampling an analog signal at a certain time. And that means you can use mechanical changes, moving any reflections in a position where the sampling won't hurt it. You can do pre-distortions via FIR filters in order to take care of the attenuation and make sure that that operates at the video sample rate, so you can correct every single sample. So here's an example of a trial run that was run for a FIR filter to make sure that the attenuation was taken care of. So here in the top is a training run of the filter to get the taps correct. Here's the input signal that we intend to transfer to the display driver, and below here is the output value. And you can see there's quite a bit of attenuation. It's lower than it should be, but by applying the filter, we get the correct value. And make sure that the correct value is the moment where here the gray sampling bar is drawn in. At that same point here, we need to be sure it has the correct value. We don't care what the other values do and how the pulse shape changes over time, as long as the value at the exact sampling time is correct. And we can prove that that is correctly implemented in the FIR filter. We did one further step. We made a completely independent ab initio model from a transmission line transferring analog signals from beginning to end. So this is our transmission line. The input is on one side. This conductor is 35 microns in width, and they're spaced 1 millimeter from each other and from the ground planes on both sides and top and bottom. And then we had noise simulation with realistic values. We used well, I won't read all that to you, but we used the noise parameters and the distortion parameters as listed below. And the initial result looks like this. So we had SAVT with noise and distortion. So without noise and distortion, everything's fine, right? So no fun looking at. So SAVT with noise and distortion, and SerDes with noise and distortion. The difference between these two is we're running this at the actual sample rate of SAVT, which is 400 megasamples per second. And this one is run at the sample rate for digital transmission, which is 4 gigasamples per second. There are a couple of things remarkable. So here is the direct input to output. There is the attenuation. It's a bit difficult to see, I'm sorry about that, but here's the input, and then because of the attenuation, this goes up a little bit. This is only the negative part of the transmission, negative voltage part. And so you see some attenuation, but after a linear correction, that attenuation is completely corrected, and we're pretty close within 2 or 3 bits of the desired value. There's also a fair filter corrected version of this, which is even closer to the output. I haven't got the data to show you here. And here you see the normal digital transmission with the same noise characteristics. And you see that it doesn't look quite good already. It looks pretty reasonable, and probably here's the best place to look at the low bit change per pixel areas. So if your pixel value is 0, then you don't have any positive to negative swings in the bit transitions, and it looks pretty good. But as soon as there are more transitions within a single digital pixel, so ones and zeros are alternating, then you can see here that the actual target value is not achieved, and there are more and more bit errors implemented in the transmission. It's safe to say that here the image is not transferred. So the digital system does not transfer the image, whereas the analog system transfers the image correctly all of the time. I've also added some bit eye diagrams of what the simulation shows. I'm not quite sure why it's not symmetric like it should be, but this is what it roughly indicates. So here, without noise, the bit eye is reasonably well defined and is transmitting a correct image. With noise, the bit eye shrinks to a level where it's not recognizable anymore, and in this case, it would display no signal. So, all in all, the transmission errors were also evaluated. So again, this is for the simulated system, not the actual system. And at the top, you see the SAVT results. So for this, as I said, without FIR filtering, you can see that the results for any bit value is approximately 10 bit values away, so 10 out of 1,000, and the standard deviation is about the same, so that looks like good transmission. And here is the digital transmission, where you see that you got 5 times, 6 times the error range. So I'll add a not surprising conclusion maybe. So SAVT delivers unprecedented visuals, as I said, higher resolution, because you can actually transfer more pixels, faster frame rates, you can do it faster, and increased image bit depth without any visible transmission errors. Color becomes a lot better because you can now accurately reproduce the color mapping that is required for a high performance, high resolution display. And, well, maybe unnecessary to show, we can do much, much higher refresh rates than digital transfer. I haven't discussed about that, but manufacturing efficiency is also increased because basically it eliminates all needs to change display driver ICs or D2A converters from display panel to display panel. And hardware economics is better because we don't need any EMI shielding, which is also a problem with current digital display drivers. So with that, I'd like to conclude. Thanks very much. We have been visible in booth number 228, but unfortunately, that's beside the point. So any questions, you can ask me now. Thank you.
Thank you. We're open for questions.
Sorry. Hi, hello, I'm Kyung from the Samsung Electronics. Thank you for your presentation. It's very good video, good critical presentation. I understand that your HYPHY system send the analog signal from the T-con to the driver IC, so
Yeah.
it's completely different to our current interface system. My question is, I agree that the people doesn't know the random noise. People may not know the noise pattern, but I just want to know in your HYPHY system, any special killer pattern is here, or no?
Actually not. Actually not, no. On the show floor, we showed a system that actually transmitted the signal across a long, just unshielded PCBA with a number of long, unshielded flex cables in between. And we also show that video signal arrives from the video source to the monitor that was showing the video signal undistorted. So, and we challenge people to put their phones on it and do anything with it. There's no way to interrupt that signal, and we don't need any precautions for that.
Oh, okay. One more question. I understanding that you add the FI filter for filtering any noise. Am I right?
I'm sorry, can you repeat?
You add the FIR filters in your IC to filtering the noise. Am I right?
Actually, no.
No.
So the only thing our IC in principle does is, well, maybe the answer is yes or no, but our IC actually does transmit the analog value from A to B. What we're trying to do is to do a FIR filter, so implement an FIR filter for various reasons. One of the reasons is to minimize the distortion of the final signal. And distortion may also be attenuation. So we know that every transmission line has a certain attenuation for the length. This is known from the very beginning, so you can design in the attenuation value. But we are now using the FIR filter also to correct for the attenuation.
Thank you.
Do you actually need to characterize the channel to come up with the FIR filter?
Which channel, sorry?
Like the link channel. Do you need to characterize the link channel to do the correction?
Yeah, to a certain extent, of course, you need to understand the channel. But as I showed you in the simulation of the ab initio system, we've got much more sophisticated models to define the channel. And so I didn't want to use those because they give you much more sophisticated answers, but they're usually also more difficult to understand. Okay. So we used a very simple model to demonstrate the behavior of the transmission line under the FIR filter. And yeah, the actual real model, if you want, we can share that at a later stage. But.
Okay. Yeah, thank you. Let's thank Alex again